And yeah, I'll let you introduce yourself. So please go ahead.
Okay. Yes. Welcome everyone. My name is Claes Strandgaard, and I work at the Department of Applied IT at Chalmers University of Technology in Sweden, Gothenburg, Sweden, and also at the Philosophy Department at the University of Gothenburg. Can you hear me? Yeah. Okay, and so I'm going to give two short presentations, and the first one is about integrating symbolic and sub-symbolic reasoning. The other one is also about integration. So let's start with this. What do we want? What kind of properties do we want our AGI systems to have? Well, probably a lot of them, but here are two that are already causing problems, I think. They should be autonomous and they should be versatile, able to do many different things. So I'll explain what I mean by those things. So autonomous means that the system mustn't be reprogrammed once it has been shipped, delivered to the user. So that means, as far as I understand, that the reward system is not going to change after the system has been shipped. So we're going to have to use one and the same reward system all the time. But on the other hand, the user may train the system anytime for specific purposes. So this is a bit similar to a dog that you can teach to train to fetch the newspaper, for example. Then you use the existing reward system. You don't redefine or reprogram the reward system or anything else. You don't do brain surgery on your dog when you train it. Right? Okay, and another thing is that we want the system to be versatile. And that can be decomposed into many different things. So we want it to support a lot of different types of learning. For example, online learning, one-shot, lifelong learning, sequence learning, inductive learning, representation learning, or also called feature learning, supervised, unsupervised learning, and reinforcement learning. There are probably other ones as well. So this is a long list of desiderata. And on the reasoning side, we also want it to be versatile. So we want it to support both symbolic and sub-symbolic reasoning or computing. And I'll explain a little bit what I mean by that. It's basically the same thing as we heard when John Laird described System 1 and System 2. So here is an example of symbolic reasoning, for example. What is 36 times 3? So that takes a while to figure out. And if we look at computer systems that handle reasoning of that kind, it can be usually things like rewrite systems, production systems, theorem provers. And here's another question: who is this on the photo here? That's when you don't have to look very long if you recognize the person. You know it immediately. So this is an example of System 1 reasoning or computing. Who is it? Do you know that? Yes. Almost Billy the Kid. Yeah. So that's the type for tasks like that. Completely different computer models are used. For example, deep networks, as we have seen lately, and for other types of sub-symbolic reasoning, reinforcement learning, for example. And this distinction, although it's a bit hard to define exactly, has been studied a lot in many different contexts by Kahneman, for example, as we heard, and by William James. Talked about associative and analytic reasoning, and it actually goes back all the way to Aristotle and Euclid. We talked about associative reasoning and axiomatic reasoning. So these are old notions. And as far as I understand, we are still facing the problem of integrating the two in a nice way. So here is a quote by 3 of the deep learning founders. Ultimately, major progress in artificial intelligence will come about through systems that combine representation learning with complex reasoning. So they said that last year, and assuming that they are right, we still need to do some work to integrate those two kinds of reasoning. So that's what we are trying to do, and we are inspired by the sea turtles here. They are interesting because they are solitary animals, so that's the antonym to social animals, right? They spend most of their lives on their own. So they hatch. When they're in the egg, inside the egg, the egg hatches, and then they make it to the sea, and they swim away, and they never get to see their parents. And then when it's time to complete the circle, they go up to the same beach often and lay their eggs. So somehow they learn to adapt to new environments on their own without anyone there to show them, without anyone being there to show them. So how do they do that? Well, the turtles, they have different needs. For example, they need glucose, water, and oxygen. And how do they know the status of those needs? Well, they have receptors inside their body, interoceptors, that will tell them the levels of those substances. And when the levels get too low, they will be prompted to take different actions to get the levels up again, for example, by eating, drinking, and breathing. Okay, so the turtle has a number of actions at its disposal, so it can eat, drink, breathe, sleep, and so on. And to stay alive, it has to take those actions continuously, otherwise it will die. So it has to satisfy those basic needs. So our system is inspired by that, and this is just an outline of some the main ideas that go into the system that we built. So the system uses a long-term memory for sub-symbolic reasoning and a working memory for symbolic reasoning. And we use a special kind of network, homemade kind of network that we call transparent networks for modeling the long-term memory. And this enables us to develop deep networks gradually using online learning, not batch learning as is the most common for deep learning. And all the sensors are Boolean, and some of the sensors are interoceptors that will reflect the status of the needs. And they are Boolean because we imitate neurons, and a neuron will either fire all out or not fire at all. So it's 0-1 situation. And the environment is modeled as a continuous stream of assignments to the sensors, those sensors that fire at a given moment. And then the system has one fixed goal that never changes, and that only goal is to survive. And it will survive by keeping its needs satisfied. So we never change those goals at all. We never change the reward function. And that was one of the requirements for an autonomous system. Okay, so now I'll tell you a little bit about how memories are stored in the long-term memory, so in those transparent networks. So they can be used for expressing MDPs and more than that as well. So for example, they can express sensory combinations like tastes, smells, pixels, temperatures, pressures, and so on. And they can also represent sequences like text, music, motions, and so on. And we also, like in ordinary MDPs, we can represent status changes like rewards of different kinds, how the different needs are affected by the transitions. And we make predictions that when we are in a certain state, then we'll go to another state with a certain probability and keep track of the status changes there. Okay, so now I'm going to, instead of defining these networks formally, which is a bit boring, I'll give you several examples so you understand how they work, roughly. So here at the bottom you see 6 sensors, and they are sensors for different kinds of tastes, like low or high sweetness, sourness, and bitterness. And then we just make, we AND a few of those together, and that will be the characteristic of a certain apple taste, for example. So the top node there will fire if we feel an apple taste. And here's another one. This is how we represent sequences. We use special nodes called delay nodes, and here we will perceive the right top node will fire if the sequence apple has been perceived. And we also have motors, as in this simple Reichenberg vehicle, where the sensors connect directly to the motors. And here's another thing with, it's the same apple again that we saw before, the apple taste network. And then once the apple taste network gets activated, we can choose between 2 different actions, for example, spit out or swallow. And here we have a network that encodes a rewrite rule. So the lower network says that, well, we'll fire when the sequence 3 + 2 has been perceived. And then one may choose the action to write 7. And then there's a prediction that in that case we will also read 7, and that will happen with probability 1, and the reward when we do that will be 0.2 or something like that. We were rewarded sometime a long time ago when we did that correctly, so that remains. So this is a way of encoding rewrite rules, which are the key to symbolic reasoning in our version. Okay, so zooming out now and looking at the system components. We have the long-term memory. We just saw it's a labeled graph, and more precisely a transparent network. Then we have an activation set, which will be a subset of the nodes, namely those nodes that are active at given moments. And we also have a status vector, which measure the level of satisfaction of the needs. And that one will be a vector in 0, 1 to the power of n that will be computed from the activation set. So those are like gauges that tell us the status of the different needs. Then we have one set called the attention set, and that's a small set. It can consist of max 1 node, and that's the node where the attention will go. And we also have an action set, which also consists of max 1 node. So if we choose to take an action, then we do that by activating a certain action node. And finally, we have a working memory, which is a sequence of say, max 7 nodes. And each of these components has its own update module. So you see that this is just a purely mathematical thing. It's a labeled graph, and then some subsets of that graph, basically. Okay, and then we also want our model to have bounded rationality. So we use fixed limits for the long-term memory capacity, like 10 to the power of 6 nodes, for example, and the working memory limit, as we saw, max 7 nodes in that sequence. And we also use bounded time for our decision-making and for the updates in general. And the bounded time, the time available would depend on the status vector. So if we're in a desperate situation, for example, some gauge is very low, some level is very low, then we have less time to reflect. Okay, and then here are some learning mechanisms, and there are quite a few of them. But remember, we wanted our system to have a lot of to meet a lot of the desiderata, so that's why. So we have Hebbian learning, first of all, that happens at random moments, and that will have the effect that frequently occurring sensory combinations will be remembered. And we also have emotional learning of state action pairs when they are emotionally, in situations that are emotionally strongly positive or strongly negative. So in a very positive situation, we want to remember it so that we can do that action again and get reward once more in the future. And if we get a lot of punishment, we want to remember that too, because then we want to avoid instead getting into that situation in the future, doing that action in the future. Okay, and then we also have imitation learning, so that stimuli such as words and melodies can be reproduced. And novelty learning, and a special case is motion, so rewarded when we move, when stimuli change. And we have abstraction learning and compression learning that improve or generalize the structures that we have. And structure is, of course, a subgraph, simply. And finally, we have forgetting, so that we can remove emotionally irrelevant structures. So those are the basic mechanisms that operate on the network. And together, these mechanisms will cause the long-term memory to evolve over time. And the result will be a deep, transparent network. All right. Okay, so now we can show how we do reasoning. And we have the sub-symbolic reasoning here, and that will be just a path in the MDP. Remember that the LTM here is also MDP. So it would be like a plan. You go from one state to another using certain actions, and you keep track of the reward that you get and the probabilities. And symbolic reasoning, then you can use the rewrite rules and replace content in the working memory instead. So you can do both kinds of reasoning here. So this is the main loop, and here this is inspired by Dave Aha, the observe, orient, decide, and act loop. So yeah, observe, you read the input, and then you orient yourself by using symbolic reasoning. So the first thing is to take in the input and then make an effort to compress the inputs, compress the working memory, and that means doing a symbolic computation. And then the next phase is to decide what to do, and that's a planning process, and that planning process will use this compressed working memory content as its starting point. And then finally, the act phase, when the selected action that was decided will be taken, if any. Okay, so we have this situation here, like the turtle is reflecting about what to do by analyzing an MDP. First it compresses the working memory content, and then it plans for survival. Does that all the time. Okay, and then this system we can use in two different ways. One is like a wild dog. We can leave it alone. We don't need to influence it at all. It will develop itself in a given environment. Or we can train it, so we can provide it with treats and have it learn different tricks, like an ordinary dog. Yeah, so this prototype can do symbolic reasoning by using ternary writing, basically. It can do sub-symbolic reasoning and some simple classification and reinforcement learning. And it builds deep networks dynamically. And it uses online, one-shot supervised and unsupervised learning, for example. So you can look at the code if you want, if you're interested, and also at some examples in our paper. Okay, so yeah, that's basically it. So then I'm going to move on to the next talk immediately then.